In this set of notes, we're going to continue looking at how to find derivatives. Specifically in this video, we're going to look at both the product rule and the quotient rule. The product rule will help us when we're looking at a product of functions, and the quotient rule will help us when we're looking at a quotient of functions. So we'll start with the product rule. So here in this box we have the product rule summarized for us. So the product rule says if we can write a function as a product of two other functions, and both of those functions are differentiable, then the derivative of the function, which is the product of the other two, is equal to the derivative of the first function times the second, and the first function times the derivative of the second function. Now notice the use of h, f, and g here are arbitrary. We could use different letters there or in different order. So the really important thing is not so much to remember that it's h is equal to f prime times g, but more so to remember if you have a function that's equal to the product of two other functions, then the derivative of that function is equal to the derivative of the first times the second function plus the first function times the derivative of the second. Another common notation that you'll see is the functions will set them equal to u and v, and then we have the exact same rule here. And so I will use both of these types of notations so you can see what they look like. All right, so we're going to look at some different examples. So the first example we have here says find the derivative of f of x is equal to the product of x to the fifth plus 1 times 4x to the third plus 1. So notice here we have obviously our function is equal to the product of two other functions. So here I'm going to let g of x be equal to x to the fifth plus 1, and I'm going to let h of x be equal to 4x cubed plus 1. And so notice that f of x is equal to g of x times h of x. And both of those are differentiable. We're going to be able to use both the product rule, or sorry, not the product rule, but the power rule, as well as the fact that we have the addition or the sum of two separate functions here. So in other words, we have 4 times x cubed plus 1, so we could split that derivative up using the derivative rules that we've seen previously, and then 4 is a constant, it can come out. So notice at this point, as I go to find these different derivatives, I am going to simplify. I'm not going to write out, each of the rules that I'm applying to find them, but do know that I am applying all of those rules from the previous 3 sections. So if I want to find g prime of x, that's going to be equal to 5x to the fourth, and h prime of x is going to be equal to 12x squared. And notice this comes from, again, we're using that power rule. I've got x to the third and h of x, so I have 3 times 4 out front, and then we take the power down by 1, and then of course the derivative of 1, since it's a constant, is 0. So therefore, by the product rule, we have that the derivative of f of x is equal to the derivative of g of x times h of x plus g of x times the derivative of h of x. And so this is going to be 5x to the fourth times 4x to the third plus 1 plus g of x is x to the fifth plus 1, and then times the derivative of h is 12x squared. And then we'll want to make sure that we always, simplify and multiply out. So here we have 5 times 4 is 20, x to the seventh plus 5x to the fourth plus 12x to the seventh plus 12x squared. And so this is going to be equal to 32 times x to the seventh plus 5x to the fourth plus 12x squared. And remember that whenever we write these expressions, we usually, once we do the rearrangement, we do order the terms by their power from highest power to lowest power. All right, so let's look at another example. So notice here we have x to the fifth plus 1 squared. And so recall that if we're going to square this, this is really equal to x to the fifth plus 1 times x to the fifth plus 1. Now we are going to see in the next section there's another way to take this derivative. So let's say we had x to the 10th even. So we're going to see other ways to work with this derivative as well in the future. So just keep that in mind. So here I'm going to write this as y is equal to x to the fifth plus 1 times x to the fifth plus 1. And the reason for that is I want to be able to show you how to use that u and v notation that was in the box on the previous page. So here I'm going to let u be equal to x to the fifth plus 1, and I'm going to let v be equal to x to the fifth plus 1. And again, that's because these are the two functions that I have the product of here. U prime is going to be equal to 5x to the fourth. V prime is going to be equal to 5x to the fourth. And therefore y prime, or the derivative there, is going to be equal to u prime times v plus u times v prime, which is equal to 5x to the fourth times x to the fifth plus 1 plus x to the fifth plus 1 times 5x to the fourth. Notice this is equal to 2 times 5x to the fourth times x to the fifth plus 1. And then this is going to be equal to 10x to the ninth plus 10x to the fourth. Right, we have yet another example here. So we have x to the fifth plus 1 squared times 4x to the third plus 1. So again, we have the product of two different functions. So if we want to set this up, we could write it as y is equal to x to the fifth plus 1 squared times 4x cubed plus 1. So again, I'm going to use that u and v notation. So here I'm going to let u be equal to x to the fifth plus 1 squared and v be equal to 4x cubed plus 1. I don't really need those parentheses here. And so notice for u prime, well, x to the fifth plus 1 squared, we just used the product rule up here to find that derivative. So that's equal to 10x to the ninth plus 10x to the fourth. And then v prime is going to be equal to 12x squared. So what you can see here is that in order to find this derivative, we actually are applying the product rule twice. The product rule was applied up above to find the derivative of u, and then we're going to apply the product rule again to find the derivative of y, or the derivative of f of x. And so on the next example, we're going to actually see how to expand the product rule. But for right now, let's continue with this example. So y is going to be equal to, or probably y prime is going to be equal to u prime times v plus u times v prime, which is going to be equal to 10 times x to the ninth plus 10x to the fourth times 4x cubed plus 1 plus x to the fifth plus 1 squared times v prime, which is 12x to the square. All right, and then from here you would want to simplify this. And I will leave that for you to do on your own. All right, so another example here. So as I was alluding to with the previous example, notice that f of x is equal to the product of three functions. So can we generalize the product rule? Now we just saw in the other example that we really did apply the product rule twice, and we were able to take the derivative of something that was the product of three functions. And so let's look at how we could generalize the product rule. So notice if y is equal to the product of three functions, all of which are differentiable, that we could use parentheses and rewrite this as u times v times w. Well, applying the product rule, and I'm just going to make a note here, just so we don't forget. So again, applying that product rule, notice that y prime would be equal to u times v prime times v plus u, oops, sorry, let me restart that. Y prime is going to be equal to u times v prime times w plus u times v times w prime. And so that's just application of the product rule if we consider the product of u and v to be one term. And that's exactly what we did on that previous example. And then we can apply the product rule a second time. And if we apply the product rule again, notice that y prime is going to be equal to, well, I'm going to use the product rule to find the derivative of u times v. And applying that product rule, I know that the derivative of u times v is u times v prime plus u prime times v, or you could switch these two terms, times w plus, and then we don't need the product rule to take, for this second term, so it just stays as it is, uv times w prime. And so notice that this becomes u v prime w plus u prime v w plus u v w prime. And so if we look at, each of these terms here, we really kind of get what we should expect intuitively. So for each of these terms, we have a u and a v and a w, but we're switching which one we take the derivative of. So for example, in the first term, we take the derivative of v, the second one, the derivative of u, and the last one, the derivative of w. So here, for this particular example, we have that u is equal to x squared plus 2, and again, that's coming here from the very top. V would be equal to x minus 3, and w is equal to 4x cubed plus 1. We could find the derivative of each of these. And then to find y prime, we could just use this piece right here and plug those values in. And again, I'll let you do that on your own. All right, so that is the product rule. And again, the product rule helps us find derivatives when we have the product of functions. We also have the quotient rule, which helps us take the derivative when we have the quotient of two functions. And so you can think of the quotient as just being the ratio of two functions. So here, if our function is equal to the quotient of two different functions, now notice that the function in the denominator, we do need that to be non-zero, and that's because we can't divide by 0. And just like with the product rule, we do need both of those derivatives to exist. Then the quotient rule says that the derivative of h of x is equal to the following. So notice in the numerator, you actually have the piece from the product rule, but then we need to divide by g of x squared. And your book provides a proof of the quotient rule and where this comes from, and so I suggest that you read this on your own. And then just like the product rule, we could alternatively write this using U and V. All right, so let's look at a couple examples. So we're going to find the derivative of f of x is equal to x squared plus 3x minus 4 divided by x plus 1. And so notice that f of x is equal to the quotient of two functions. So here, let's let u be equal to x squared plus 3x minus 4. And let's let v be equal to x plus 1. Notice that both of these are differentiable. U prime is equal to 2x plus 3, and v prime is equal to 1. And then since we could write our overall function as y is equal to u over v, we get the following derivative. So y prime is going to be equal to, we'll kind of write this up here first. So again, I'm going to be applying this rule right here. I'm going to have u prime times v minus u times v prime divided by v squared. Now, one thing that I should have noted that I didn't earlier is I said that this top piece looks like the product rule. And it does look like the product rule, but there is one important difference here. Is notice here in the numerator we have a negative sign, whereas when we took the product rule we had a positive sign. So it is similar to the product rule in the numerator, but there is that difference. Alright, so now we can plug these values in. So y prime is equal to 2x plus 3 times v, which is x plus 1, minus u, which is x squared plus 3x minus 4 times v prime, which is just 1. And then we're going to divide all of this by v squared, so x plus 1 squared. And then, as usual, we do want to make sure that we go through and we simplify this as much as possible. And so what you will typically find is you're going to be able to simplify the numerator, but not always the denominator. So here, if we go through and simplify, you should find this is equal to x squared plus 8x minus 1 divided by x plus 1 squared. All right, so here is another example. So here we have that f of x is equal to minus x cubed plus 2x squared plus 3 over x to the fourth plus 1. So first of all, notice what we've got is we've got one term plus a second term. And so we saw previously in our notes how to handle a derivative when we have the sum of two functions. And so that's what we're going to want to do here. We're actually going to want to apply that rule from the previous section. Since we have the sum of two functions, we can use the power rule to find the derivative of the first term, and then the quotient rule to find the derivative of the second term. So let's see how we can do this. So what I'm going to do is I'm going to actually find the derivative of the first term and the second term separately, and then I'm going to add them together. So for the first term, I'm going to apply the power rule. And so I can see the derivative of that first term is negative 3x squared. I'm going to write with derivative with respect to. You will commonly see WRT means with respect to, and we're taking it with respect to x. And then for the second term, let's apply the quotient rule to take the derivative with respect to x. And so here, I'm going to let y be equal to 2x squared plus 3 over x to the fourth plus 1. So in this case, u is equal to 2x squared plus 3, v is equal to x to the fourth plus 1. U prime is equal to, and again we're going to use that power rule, 4x, and v prime is equal to 4x cubed. Now applying the quotient rule. So remember, for our quotient rule we have u prime times v minus u times v prime divided by v squared. So plugging this in, we're going to have 4x times x to the fourth plus 1 minus 2x squared. Oops, I'm running out of room here. Plus 3 times 4x cubed all over v squared, and in this case v squared is equal to x to the fourth plus 1 squared. And again, we could go through and simplify. So if we were to simplify the numerator, we would end up with minus 4x to the fifth minus 12x cubed plus 4x, all divided by x to the fourth plus 1 squared. So then, if we want to find the derivative of f of x, so remember that was our overall function that we had up top, that's going to be equal to the derivative of the first term, which is negative 3x squared, plus the derivative of the second term, which was minus 4x to the fifth minus 12x to the third plus 4x divided by x to the fourth plus 1 squared. So one thing that's really important is if you're going to break your derivative up into second steps, using verbiage like this is really important because it lets your reader know, hey, I'm going to break this into the two terms. I found the first derivative first, or first term's derivative first, the second term's derivative, and then we can say combining, or probably even better than saying combining, then we could say then applying the rule for sums of functions. So that way it makes it very clear to your reader that here, you're taking that overall derivative. And it's important, that also notice here I've used y, but I've defined what y was equal to. We can see that I'm using y just for that second term. So we want to just make sure we're always consistent and it's really clear what our different steps are. All right, so we've got one more. So here we're going to find the tangent line at the indicated point. So this is very similar to problems that we've seen in the past. And so remember that the derivative evaluated at a point can tell us what the slope of the derivative is at that particular point. And so here we're going to go through and we're going to end up using some of the rules that we've seen to help us find this derivative. And then that's going to help us find the tangent line at that indicated point. All right, so starting out here, what I'm going to do is I'm going to actually rewrite this. Instead of looking at the sum of quotients, I'm going to actually rewrite these as powers so that I can write the power rule. Now you could keep these as quotients and use the quotient rule for each of these terms separately. You would get the same answer. I tend to like to use the power rule. So I'm going to rewrite this as f of x is equal to x to the minus 1 minus 2 times x to the negative 1/2 plus 4 times x to the minus 2. And then I'm going to apply the power rule. Now your book, when we first defined the power rule in the previous section, it said that the power rule was valid for any constant in that exponent, but it only looked at the proof when that constant was positive. Your book shows that we can expand that power rule to have negative exponents using the quotient rule. So in other words, we expand that proof, and so I do suggest reading that section of the book so you can see where that comes from. So applying the power rule, we have that f prime of x is equal to negative x to the negative 2 plus, now notice here for this second term, what I'm going to do is I've got a negative 2. I'm going to bring down the negative 1/2 exponent. So negative 2 times negative 1/2, that just gives me a 1. So I've got plus x, and then minus 1/2 minus 1 is equal to minus 3/2. And then for the third term, applying the power rule, I'm going to have negative 2 times 4 is minus 8. And then if we subtract 1 from negative 2, we have negative 3. So this gives me the derivative, and so again, remember that the derivative can help me find the slope of the tangent line. I'm interested when x is equal to 1. So what I need to do is I need to do two things. The first is I'm going to evaluate the derivative. At x is equal to 1, and this is going to help me find the slope of the tangent line. So here we have f prime at 1 is equal to minus 1 to the negative 2 plus 1 to the negative 3/2 minus 8 times 1 to the negative 1/3. So this tells me that f prime at 1 is equal to negative 8. And then we're going to evaluate the function at 1. And this is to help me find a point the tangent line passes through. Okay, so here f of 1 is equal to, going all the way back up to the top, we're going to have 1 over 1 minus 2 over the square root of 1, or I could have also used it using the powers, plus 4 over 1 squared. Let me minimize that. There we go. And so that's going to be equal to 1 minus 2 plus 4, which is equal to 3. So therefore, the tangent line and we're going to, again, going back to one of those previous sections where we saw how once we have a point the tangent line passes through and the slope of the tangent line, we could write that as y minus f evaluated at the point is equal to the tangent line. Oops. We're going to snooze that right now. We do not want to restart. The tangent line evaluated at the point, the derivative evaluated at the point times x minus 1. And so this gives us y minus 3 is equal to minus 8 times x minus 1. Or we could write this as y is equal to negative 8x plus 11. And that gives us that tangent line. So this concludes this set of notes. So as always, if you have any questions, please let me know.